Okay, good afternoon, everyone. In today's lecture, we will be starting a new topic. In today's lecture, we will start the electricity from textbook section 19.1, 19.4, where we'll be studying electric charges and force exerted between those charges. In next lecture, we will be looking at electric field around the charge and the electric field lines. Okay. So Benjamin Franklin, who was a scientist, conducted several experiments on electricity, and he hypothesized that only two types of charges do exist: positive and negative charges. He conducted a very famous experiment using a kite with a key hanging, and he put it in the sky in a rainy day where there were some thunderstorms. Luckily, he was not struck by a lightning at that day, but he figured out later on that that key was charged due to the transfer of the charges from the clouds to the key. So what do we know today about those charges in atoms in the material? So we know that an atom consists of a nucleus. This nucleus has protons and neutrons inside, where the mass is way heavier than the electrons that are surrounding this nucleus, making a cloud. So in the nucleus, we have the protons that are positively charged. We have the neutrons that are neutral, zero charges. And outside the nucleus, we have the electrons that are negatively charged. Now, the charge of one electron, the magnitude of the charge of one electron is 1.602 10 to the power minus 19 Coulomb. And this is the same magnitude of the proton's charge. So the proton and the electrons, they share the same charge magnitude. The signs are different. Protons are positive and electrons are negatively charged. What is the unit for the charge in our course here? We'll be using the International Systems unit, which is basically Coulomb. So the charge, the unit of the charge that we will be using is Coulomb, denoted by C. So you can see that this is the nucleus that has the protons and the neutrons inside. The mass is way more than the masses of the total electrons in the electronic cloud. So if we have those charges that are from two types, positive and negative charges, then according to Coulombs law, there will be forces exerted from one of those, from this charge on the other charges. So what is the relationship that governs the magnitude of this force between two charges? So we'll be looking here at two charges as the least number of charges. You need at least two charges to have a force. Why? Because the force itself is due to the contribution of both the charges. So if we look here at the Coulombs law, this is the magnitude of the force. We will see that this magnitude of the force depends on the magnitude of the two charges at least that results into that exerted force. So if I am to have those two charges, Q2 and Q1, charge Q1 will exert a force on charge Q2, and charge Q2 will also exert a force on charge Q1. The magnitude of this force is the same. Why? Because if you look at the expression, for both forces, you will have Q1 and Q2 in the numerator. As we will see later on, it is very important to keep in mind that if you have two charges, one of them is exerting a force on the other one, the forces exerted by both have the same magnitude. They're equal in magnitude. So we're going to come to an example where we see those forces exerted by charges on each other. Now, also something to keep in mind that alike charges, they repel. So charges that are from the same type, they exert a repulsive force. They tend to push each other far away. Opposite charges attract, which means if you have two charges from the opposite types, they tend to attract each other. One of them will exert a force such that it is attracting the second charge to it. And the second charge also will exert a force on the first one such that it is attracting this charge toward it. Magnitude is the same. So let's look at this example in order to understand how do those forces behave. If I have two spheres, that those two spheres, both of them are charged with positive charge. Sphere number 2 has 3 times the charge of sphere number 1. Which diagram correctly shows the electric forces that the spheres exert on each other? Again, I have a Q2 here. That is a 3 times Q1. So magnitude-wise, they're from the same type, they're alike charges, but magnitude-wise, Q2 is a 3 times Q1. Which one is the correct representation for the exerted forces? Is it 1, 2, 3, 4, or 5? Yes. Okay. Colleague is saying 5. Yes? 2? Yeah. Okay. So we have so far 2 and 5. Are those, yes? 3. 2, 3, and 5. Any other answers? Or, yes? That's correct. So this would be the point that I would start off thinking about those forces. So the first thing that should come to your brain is the magnitude of those two forces should be the same. So if we are to look at the force here and the force here, are they of equal magnitude? No. So 2 is wrong. What about 3? Do they have equal magnitudes? No. So 3 is also wrong. What about 5? Yes. So the correct answer is 5. Don't let the value of the charge trick you here, because you saw Q2 is a 3 times, or Q2 is a 3 times the Q1. You would think that the force should be 3 times. No. Because the force for both of them is the contribution of the product of a Q1 and a Q2. So you have a Q1 and a Q2 in both expressions, for the first force and for the second force. Just keep in mind that the magnitude between two charges that are exerting forces on each other should be the same. What determines the direction of the force is either being alike or opposite charge, opposite polarity. Make sense? So the answer is 5. So let's move on to this example. In this example, we have two ping pong balls that are set on a table separated by 1 centimeter. Both have been charged. The first has a charge of 1 times 10 to the power minus 9 Coulomb, positive. So the first ball is positively charged. The second has a charge of minus 3 10 to the power minus 10 Coulomb. So it's negatively charged. Now, magnitude-wise, which one is greater? The 1 to the power minus 9 or the 10 to the power, or the 3 to the power minus 10? The 1 to the power minus 9, magnitude-wise, is greater than the 3 to the power minus 10. Okay. So what do we need to do? We need to calculate the magnitude of the electric force between these two ping pong balls. Now, in this course, those ping pong balls, we'll treat them as dots. We are not interested here in the volume of this ping pong and how the charges are distributed. We're treating those ping pong balls here as dot charges, point charges. So treating them as pointed charges basically means that if this is my table, and let me use here the colors just to distinguish between Q1 and Q2 and the forces exerted by Q1 on a Q2. So let me use a Q1 here as red. So this one is 1 to the power minus 9 Coulomb. And the other one is green. Q2 is minus 3, 10 to the power minus 10 Coulomb. Now, I need to draw the force exerted by Q1 on a Q2. So I am drawing it on a Q2 because Q1 is the one that is exerting it. The first thing I need to look at before I draw the force is what type of charges are those? Are those two charges alike or opposite? If they are opposite, then I have to do it an attractive. It will be pointing toward the one that is exerting it. So since Q1 is positive and Q2 is negative, the force exerted by Q1 on Q2 would be attractive, which means pulling it toward the Q1. And I would call this one F1 to show you that this F1 is coming from Q1. Now, the force exerted by Q2 on Q1 should have the same magnitude, however, opposite in direction. It should be also attractive, right? Because both are from opposite signs. So in this case, this one is F2 due to Q2. Okay, so now I know which force belongs to which or caused by which, but keep in mind that F1 magnitude equals to F2. So if I want now to calculate this magnitude, this force, I can say F1 magnitude, this is also equal to F2 magnitude, equals to K times Q1 times Q2. Notice that the Q's here are magnitude divided by R squared. So if I have here Q1 as 1 to the power minus 9 Coulomb, Q2 10 minus 3 10 to the power minus 10, the distance here is 1 centimeter, which is 10 to the power minus 2 meter. So if I am now to substitute, I have 8.99 10 to the power 9, that probably here we forgot to mention that this K is called the proportionality constant, and it's given as 8.99 10 to the power 9 Newton meter squared per Coulomb squared. You don't have to memorize those numbers, as we will see also other numbers related to the masses of the proton, neutron, electron. All those numbers will be given to you in the formula sheet. So you don't have to worry about memorizing those numbers. What you need to worry about is how to apply those numbers in the given equations that will also be given to you to calculate the parameters that we ask you to do. So back to here. So K is 8.99 10 to the power 9 times the magnitude of Q1, which is 1 10 to the power minus 9, times the magnitude of Q2. Notice that I'm substituting here Q2 as positive because I'm using the magnitude. So this is going to be 3 10 to the power minus 10. And now all this would be divided by 10 to the power minus 2 squared. Don't forget the square. This is one of the common mistakes that students do when they calculate the magnitude of forces. Now, F1 magnitude equals to F2 magnitude equals to 2.7 10 to the power minus 5 Newton. So this is how we calculate the magnitude of a force for two charges that were considered as point charges using Coulombs law. So that's part A. Part B. Any question about part A? Yes. Let me come to you. That's correct. As long as you are solving for the magnitude, you'll be using magnitude. Part B, if the ping pong balls each have a mass of 0.01 kilograms, so they are the same masses, same ping pong, same masses, what initial acceleration would each experience from this force? So we want to calculate the acceleration. We've dealt with the acceleration before for a force applied on a mass, right? So what we know is force equals to m times a. Now, since the masses are equal for both ping pong balls, then the acceleration is expected to be equal because the force is equal in magnitude, which means in magnitude, I can say A1 magnitude equals to A2 magnitude. Now, all this will equals to F divided by m. Since m is the same for both laws. So A1 magnitude equals to A2 magnitude equals to 2.7 10 to the power minus 5 divided by 10 to the power minus 2, which is 2.7 10 to the power minus 3 meter per second squared. So this is the acceleration. If I want to put this acceleration on my diagram here, I can say that this is A1 and this is A2. Right? We have said before that the acceleration is in the same direction of the force. Okay. So this is how we solve for the acceleration. Any question about this problem? Then the acceleration would be different. Always remember F equals to ma. Force exerted on a mass. This mass is different, then acceleration will be different. Okay, so let's move on to the next example. In this example, we have two protons inside a helium nucleus have a typical separation of 10 to the power minus 15 meter. What is the electric force between these two particles? So this is similar to what we have done, except here we're looking at the force inside the nucleus for a helium nucleus, where I have two protons separated by 3 to the power minus 15. So in this case, if this is Q1, and remember this Q1 is positive E. It's a proton. Q2 is also a proton. The distance R is 10 to the power minus 15 meter. So what we know here that Q1 equals to Q2 equals to 1.602 10 to the power minus 19 Coulomb. So if I am to calculate the force exerted by Q2 on Q1, is it a repulsive or attractive force? Repulsive force. So if my Q2 isn't in green, then my F2 here would be pointing in this direction. And if my Q1 is in red, then the force exerted by Q1 on the Q2 would be in this direction. Draw the line between the two charges, and then on that line, the forces should lie as well. Alike charges, repulsive forces. Opposite charges, attractive forces. Now keep in mind that F1 magnitude equals to F2 magnitude equals to K Q1 times Q2 divided by R squared. So this equals to 8.99 10 to the power 9 times Q1, which is 1.602 10 to the power minus 19 times magnitude of a Q2, which is the same, and that's why I'm going to put squared here, divided by R squared, which is 3 10 to the power minus 15 squared. Just here on the side, the distance is minus 15 meters. And F1 magnitude equals to F2 magnitudes equals to 25.6 Newton. So notice that F1 and F2 are pushing, so there are, F1 is pushing Q2 away, and F2 is also pushing Q1 away, right? Now the second part of the question is calculate the acceleration. Again, the acceleration here would be the same. Why would it be the same? Because the mass of those two protons are the same. The mass is given to you 1.67 10 to the power minus 27 kilograms. So we know here that the mass of the proton is 1.67 10 to the power minus 27 kilograms, which means that the acceleration would be the same. The initial acceleration on both protons would be the same. So I can say this also here, A1 equals to A2 equals to F divided by M. And in this case, I have F as 25.6 divided by 1.67 10 to the power minus 27. And the answer is 1.54 10 to the power 28 meter per second squared. So this is the acceleration, and the acceleration is the same for both of them since the masses are the same, and I can put the acceleration here as A1 A2, pointing in the same direction of the force. Any question about this second example? Again, the direction is pointing away, pushing Q1. F1 is pushing Q2 away. F2 is pushing Q1 further away from Q2. So let's move on to this question. I'm sure many of you have experienced such a phenomenon when you have a fuzzy hair walking on a carpet or sliding on in the playground on the plastic slides a long time ago. What do you think the cause for this phenomenon to happen? Is it because a charge builds up on the child through transfer of electrons during the slide? Or transfer of protons during the slide? Or mom didn't have time to brush his hair before sliding? A and a little bit of B. So, and a little bit of C. Maybe C helped that phenomenon to be, exaggerated this way. Okay, so the answer is A, because the particle that moves, the particle that jumps from one object to another is the electron. Protons do not move. Protons are locked in this nucleus, right? However, if an electron moves from one spot to another spot, it leaves its a spot at A makes it more positive. And when it goes to the B spot, it becomes more electrons than protons, and that's why this becomes negatively charged. So the electron moving from one place to another is the one that's causing an object to be positively charged and negatively charged. So if it leaves its spot, then the number of electrons becomes less, and the number of protons becomes more, and that's why this object becomes positively charged. Now, the object that the electron went to now have more electrons than protons, and that's why this object becomes negatively charged. But protons do not move. Protons are locked in the nucleus. So be careful when you are in a mountain with the existence of lightning. Take a shelter. Don't expose yourself to unsafe condition, because that happened before, where those two kids were struck by lightning. Luckily, they survived. Okay. So let's move on to the next example in Coulombs law, where we want to calculate the force, not only the magnitude, but now the direction of this force. So in this example, it reads the following: 3 charged particles, an electron, proton, and an alpha particle. Now, the alpha particle is a helium atom that has lost 2 electrons. That's why it becomes +2, which means the total charge, it is positively charged with an equivalent to 2 protons, +2, or 2+. Okay, so we need to calculate the resultant force on the proton due to the existence of the electron and the alpha particle. So our interest here is the total force exerted on the proton, not the forces on the electron or on the alpha particle. The forces, we need to calculate the total force exerted on the proton. So the distances have been given to me between those charges, and also the angle between the horizontal and the distance between the electron and the proton. We need to calculate the resultant force on the proton. So how do we do it? Okay, let's see how do we do it. So the electron, I will give it, and I will make the electron as red. So the electron here is Q1 minus E. Then I have the proton, Q2 plus E. And then I have the alpha. I'm going to call it Q3. And it is plus 2E. Equivalent to 2 protons. So now let me draw the lines between where this one is, I'm calling R1, and this one I'm calling R2. So I have a Q1 as minus 1.602, 10 to the power minus 19 Coulomb. I have a Q2 as 1.602, 10 to the power minus 19 Coulomb. I have a Q3 as 2 times 1.602, 10 to the power minus 19 Coulomb. I have R1 as 1.2, 10 to the power minus 10 meter. I have R2 as 1.4, 10 to the power minus 10 meter. So the first thing I need to draw is the force due to Q1, which is the electron, on Q2, which is the proton. The first thing I need to pay attention to, are those charges opposite or alike? They're opposite, which means the force should be attractive force. So in this case, if it's an attractive force, then it should be pointing toward Q1. And I will call this one F1, attractive. What about the force due to Q3 on the proton? Is it attractive or repulsive? Repulsive, because Q2 is positive and Q3 is positive. Then F3 is going to be repulsive force. Now, I need not to forget that the angle here, theta, and I'll put here theta as 55 degrees. So, what's the first thing to do? Calculate the magnitude of F1 and magnitude of F3. So let's do this. So we have F1 magnitude equals to K times F1. What are the charges that goes into the equation for F1? What Q's? What charges? Q1 and Q2. So I have Q1 times Q2 divided by R1 squared. So in this case, F1 magnitude equals to 8.99 10 to the power 9 times Q1 and Q2 magnitude-wise, they're the same, right? One of them a charge of a proton and the other one is a charge of electron. Magnitude-wise, they're the same. So that's why I will 1.602 10 to the power minus 19, and I'll say squared, divided by 1.2 10 to the power minus 10, also squared, which means F1 magnitude equals to 1.6 10 to the power minus 8 Newton. Right? So this is F1. What about F3? F3 magnitude is K times, what charges goes into the F3 equation? Q2 and Q3. So I have here Q2 times Q3 divided by R2 squared, or F3 magnitude equals to 8.99 10 to the power 9 times 1.602 10 to the power minus 19 times 2 times 1.602 10 to the power minus 19 divided by 1.4 10 to the power minus 10 squared. And in this case, F3 magnitude as 2.35 10 to the power minus 8 Newton. So this is F3 and this is F1. So I found the magnitudes of both forces, F1 and F3. Now, how can I find the total force? The same thing we used to do for the velocity, if you recall. Dealing with vectors, get the components, X component, Y component for each, find the net X component, find the net Y component, that's it. Then you can find the magnitude of the final vector, and then you can find also the direction of the vector. So let's do this. In order to do this, what I'm going to do here is I will put my coordinates right on the Q2, which is the proton, the charge of interest. So I can project F1, F1x, and I can project F1 on the Y. I'm going to call it F1y. Is that right? Now I can find F1x and F1y. F1x is F1 cosine 55. F1y is F1 times sine 55. So this one, F1x is 1.68 10 to the power 1.6 10 to the power minus 8 times cosine 55, which is 0.57. And then F1y is 1.6 10 to the power minus 8 times sine 55, 0.82. Then F1x is 0.91 Newton. F1y is 10 to the power minus 8. F1y is 0.82 times 1. Is 1.31 10 to the power minus 8 Newton. What about F3x? It is F3 because all F3 is on the x-axis. What about F3y? It is 0 because F3 is perpendicular on the y-axis. So now if I look at Fnet, and let me pick a color here. So Fnet x would be the summation of F1x and F3. So now this one is going to be Fnet x. Fnet y is the same as F1y, right? Because there's no y component for the F3, so it will be overlapping here. Now, if I am to draw, remember, this is also F net y, so the force is this. This is F net. And the angle is here, phi. So in order for me to calculate F net x is F1x plus F3, which is 0.91 10 to the power minus 8 plus 2.35 10 to the power minus 8. And this would be 3.26 10 to the power minus 8 Newton. F net y is the same as F1y, which is 1.3 10 to the power minus 8 Newton. Now you can calculate F net, which is square root of F net x squared plus F net y squared. And phi is tan inverse of F net y over F net x. So this is going to be 22 degrees above x-axis. And F net is 3.5 10 to the power minus 8 Newton. So let me stop here. If you have any question, please ask. You can see me after the lecture. We have an office hour today.